1. Task Introduction. This task involves learning the basic commissioning procedures of a 6 degrees of freedom 6DOF robot control system. The goal is to understand the scope of robot commissioning and to carry out the commissioning process correctly to ensure the system operates as intended. 2. Learning Objectives. Knowledge Objectives. Grasp the fundamental aspects of 6DOF robot commissioning. Understand the meanings of zero position parameters, motion parameters, and joint parameters of the robot system. Comprehend the concepts of software limits and interference zones. Skill Objectives. Accurately set the robot's zero position, motion parameters, and joint parameters. Properly configure software limits and define interference zones. Successfully back up the robot system. Caliber Objectives. Develop team spirit and foster a collaborative mindset. Cultivate professionalism and form a rigorous and scientific working attitude. Cultivate the habit of summarizing the training process and outcomes to gain experience for future training. 3. Guiding questions. 1. What aspects are involved in the basic commissioning of a robot? Basic commissioning of a robot involves motion, safety, and fundamental functionality debugging. This includes tasks such as zero position setting, coordinate system verification, joint parameter setup, motion parameter configuration, software limit settings, interference zone configuration, system backup, and automatic homing. 2. What is the robot's zero position? In which situations is it necessary to set the zero position? Zero position setting involves aligning the robot's mechanical origin with the absolute value of the motor encoder in the system. The robot's origin serves as the reference point for its operation. Situations that require zero position setting include abnormal zero position after replacing the controller or servo drive, changes in the mechanical origin and encoder absolute value after replacing the motor or encoder, abnormal robot zero position. 3. What is the purpose of verifying the robot's coordinate system? The GRC Industrial Robot Control System allows calling different user coordinate systems and tool coordinate systems within programs. This feature is used to facilitate robot programming in complex working environments with multiple tools and workstations, thereby improving programming efficiency. 4. Knowledge Description. 1. Robot System Commissioning. 1. Zero Position. 1. Page Navigation. Main page. System Settings. Absolute Zero Position. 2. Robot's absolute zero position posture. The posture of the robot at its absolute zero position is as shown in the figure. The requirements are: joint 3 must be at a 0 degrees angle relative to the vertical line. Joints 5 and 6 must be at a 0 degrees angle relative to the horizontal line. 3. Operation method for setting the absolute zero position. Step 1. Use the joint coordinate system to manually teach the robot to the position shown in the figure. Step 2. Enter the absolute zero position interface. In the Modify column, select the axis to be modified or press Select All to modify all axes. Then press the Read button to read the current motor position and set it as the new zero position. See the diagram below for reference. 2. Coordinate System Verification. 1. Page Navigation. Main page. System Settings. Coordinate System Verification. 2. Through the Coordinate System Verification feature, the system can respond differently based on user settings when the current coordinate system and the top point's coordinate system are not the same. There are 3 options. First option: prohibit forward and backward movement between different coordinate system numbers. If the current coordinate system set on the robot is different from the one used at the top point, the system triggers an alarm and halts the program. For example, in the program, when it reaches the 3rd line, the system alarms and stops the program. Second option: allow forward and backward movement between different coordinate system numbers. With this setting enabled, P1 and P2 are points defined under User Coordinate System 1, while P3 and P4 are points under User Coordinate System 2. When the robot executes the following program, it will follow User Coordinate System 1 to move through points P1 and P2. Then, it proceeds to points P3 and P4. The actual motion path is shown in the diagram. The robot still uses User Coordinate System 1 as the reference. As a result, it will move to the positions of P3 and P4, instead of switching to User Coordinate System 2 for those points. Third option, allow forward and backward movement between different coordinate system numbers and automatically switch to the last top point's coordinate number. With this option enabled, when the robot executes the following program, the system automatically switches based on the user and tool coordinate system numbers recorded for each top point. The actual motion path is as shown in the diagram. After completing the movement through points P1 and P2 under User Coordinate System 1, the robot switches to User Coordinate System 2 to move through points P3 and P4. 3. Joint parameters. 1. Page navigation, main page, parameter settings, joint parameters. 2. Joint parameter settings. The joint parameters that need to be set include maximum speed, maximum acceleration and deceleration for each joint, as shown in the table. Explanation. Maximum speed refers to the joint's maximum angular velocity, degrees per second, configured based on motor parameters and mechanical characteristics. Maximum acceleration, the highest acceleration value set for a joint, unit, millimeters per second squared. Deceleration, the deceleration value set for when a joint comes to a stop, unit, millimeters per second squared. These parameters define the dynamic characteristics of joint motion by constraining the joint's angular velocity, the maximum acceleration when the joint reaches its top speed, and the maximum deceleration when slowing down from peak velocity to a complete stop. The magnitude of both acceleration and deceleration greatly affects the impact force during joint movement. 4. Motion parameters. 1. Page navigation, main page, parameter settings, motion parameters. 2. Motion parameter settings. Motion parameters mainly involve setting the acceleration or deceleration time constant, the maximum allowable position velocity, and acceleration during robot movement. Explanation. The acceleration or deceleration time constant refers to the time the robot takes to accelerate from a standstill to a set speed, or to decelerate from a set speed to a complete stop. The setting of this time constant directly impacts the robot's dynamic performance. Specific settings are shown in the figure and can be adjusted as needed. The maximum allowable position velocity of the robot refers to the highest linear or angular velocity that the robot's arm or tool center point can reach during uniform motion under load conditions. The maximum posture velocity refers to the maximum acceleration allowed when the robot undergoes changes in posture. This directly affects the robot's motion stability, accuracy, and the mechanical impact on its structure. 5. System backup. 1. Page navigation, main page, parameter settings, system backup. 2. Backup and restore of system parameters. Explanation. System parameter backup. The parameters included in the system backup cover joint parameters, axis parameters, motion parameters, link parameters, software limits, following parameters, and others. System parameter restore. This function restores the system parameters. 6. Software limits. 1. Page navigation, main page, machine settings, software limits. 2. Refers to the system's restriction on the motion range of each joint axis, including both positive limits and negative limits. The software limit setting interface is shown in the figure. Explanation. The software limits should be configured outside the robot's typical operating range, but before the mechanical limits are reached. When setting the limits, first return the robot to its home position. Then move it in the positive direction until it reaches the positive hardware limit. After that, move it back 5 to 10 millimeters in the negative direction and set this position as the positive software limit. The same method applies when setting the negative software limit, but in reverse. 7. Interference zones. 1. Page navigation. Main page, machine settings, interference zone. When multiple robots are working collaboratively, an interference zone can be defined as a spatial area where robots are not allowed to enter simultaneously. This serves as a protection mechanism. A maximum of 6 interference zones can be set. 2. Interference zone configuration. Explanation. Release all. Deactivates all interference zones. Reference coordinate system refers to the coordinate system on which the maximum and minimum values in the diagram are based. Options include base coordinate and user coordinate. User coordinate. This option is valid when reference coordinate system is set to user coordinate. It specifies the user coordinate system number used as a reference for the interference zone. Input-output signals refer to the I/O signals triggered when multiple robots are working collaboratively. Priority. When 2 robots enter an interference zone at the same time, the one with the higher priority is allowed to continue operating, while the one with lower priority switches to a pause state and waits. Maximum and minimum values represent 2 diagonally opposite vertices of a cuboid that defines the size and dimensions of the cuboid's spatial volume. These values can be obtained through teaching or direct input, as shown in the figure. 3. Function application. The interference zone is a cuboid space defined by the maximum and minimum values based on a chosen coordinate system. When creating the interference zone, first confirm the reference coordinate system, then determine the spatial dimensions using the specified maximum and minimum values. When a robot is about to enter the interference zone during program execution, and it detects that another robot is already within the zone, it will pause at the boundary of the zone and wait. Once the other robot exits the zone, and the corresponding confirmation signal is received, the robot will resume the program from where it paused. 5. Task implementation. 1. Adjust the robot's position to the 0 position, then confirm it correctly. 2. Properly set the robot's joint parameters and motion parameters. 3. Correctly perform system backup and restore for the robot. 4. Move each axis of the robot to its mechanical limit, then properly set the software limits and verify them. 5. Set up an interference zone, then run the robot to verify whether the interference zone has been correctly configured. This lecture ends here. Thank you.